Hello guys, so in this video I wanted to show you some of my X-ray tube and explain some of the difference and technological aspect that goes into the different type of X-ray application that we use nowadays. So here in front of you, you have a 4 tube. The two in the back here are used in X-ray diffraction and works a little bit differently from these two in the front. Let's start with this one. When it wasn't broken, it had the filament, so the cathode here soldered to the glass with 2 feet through. Now unfortunately it's broken. And you have the two parts of the tube, so the cathode and the anode here that goes inside. And this tube works by applying a high voltage potential to the anode while leaving the cathode grounded. So you have here the filament that generates the electrons. They are then accelerated towards the anode and they enter this copper tube and hit the anode here, which is this tungsten gray button. The reason for the copper outside here is to prevent secondary electrons bombardment onto the glass that will turn brownish, as you can see from this other tube. Here on the outside you can see the hole where the X-ray come from. So the electrons come from this side, enter it, goes to the tungsten. They get slowed down and emit X-rays by Bremsstrahlung. The X-rays then come out of this hole and goes to the target like a patient. This tube interestingly came with this LED shielding around it already, and this was probably used for some kind of medical application. And it has a glass enclosure which I don't know, has a 1 millimeter thickness, and this inherently filters out the lowest energy X-rays. This other tube instead doesn't have such a filtering because well, it works on the same principle. So you have the anode at a high potential, the cathode grounded, and the electrons strike it and emit X-rays. But here you have a beryllium window. This gray beryllium here is just there to let even the lowest energy X-rays pass, because beryllium is almost transparent to even low energy X-rays. And so this tube can be used for different applications, for example mammography, in which soft tissue needs to be analyzed, and so a lower energy X-rays is required to have a higher contrast. Also, another difference from this other X-ray tube is the cathode. While in the other tube you can see that the filament is almost flush with the surface of the cathode. In this other tube you have that the filament is inside of this focusing cup that has this particular geometry, so that the electrons are focused to a lower spot, so that you can achieve less blurry image, so you can increase the definition and see lower details, because the X-rays will be generated in a smaller spot onto the cathode, and so they will have better spatial definition. So this two tube that works in a similar way also have relatively low power consumption, because they are used in medical devices. They need to be usually operated in a pulse mode, so you send a pulse of high voltage that last maybe a few microseconds or even less. For this reason, the operation uses low power, and this allows the anode to be a high voltage potential, because the power can be dissipated through the oil in which the tube is normally placed. So both of these tubes will be normally placed inside of an oil bath with an aperture to let the X-ray through. And so the heat dissipation of the current flowing through the anode will be dissipated only due to the conduction between the metal and the oil itself. And for this reason, this tube normally have a maximum power rating of around 300 or 400 watts of power. This little tube is probably a lot less, like in the tens of watt, while this bigger one may be up to 200 or 300 watts. So this two tube differs from this other bigger here tube because unlike the smaller one, this tube works in a continuous mode and they dissipate a lot of power. For this reason, they have a different polarity approach because this two tube works with the anode, so this lower part of the tube grounded, so at a 0 voltage, while the cathode, so the filament, is at a low voltage potential of several kilovolts underground. And this is done because the anode needs to dissipate a lot of power, and so it needs to be connected to the water line, and because the water line is grounded, the anode needs to be grounded too. These two tubes have also a similar application because they are both used for X-ray diffraction. X-ray diffraction requires a lot of power due to the physical phenomenon happening. Here on the tube you can see in fact the power rating. So this tube worked at a maximum of 60 kilovolt and 2200 watts of power. That is a lot of power that needed to be dissipated. So while these two tubes have both a tungsten target, the X-ray diffraction tube usually vary in target material depending on the application. For example, this X-ray tube uses copper as the target, as you can see from this incision here. While other tube may also use, molybdenum, for example. Molybdenum is used because it has X-ray emission at 17 kiloelectron volt that is better suited for single crystal X-ray diffraction, while copper is best suited for Bragg experiment, so for example in powder X-ray diffraction. I've explained more of this detail in another video where I used this tube to perform some X-ray diffraction experiment, so if you're interested in this application and also in other X-ray imaging, you can go there. But anyway, all of this energy are really low, and they would be completely filtered off if you used a glass enclosure like in this tube. For that reason, all of this diffraction tube have beryllium windows. As you can see, they have 4 beryllium windows, all at 90 degrees from each other. And the reason, because there are 4 windows instead of only one, is that the filament inside of this tube is a coil of wire going in one direction, like this. This is a bigger representation of the coil of wire. So you have this coil at around this height that emits the electrons. The electrons are then accelerated towards the anode and strike it, emitting X-rays. And so you have these 4 windows to capture the X-rays coming from the X-ray beam parallel to the filament or perpendicular to it. Why? Because the X-ray coming from this window would have a lower diameter, because the focal spot of the filament is lower. As you can see, it's only the diameter of the filament, while the X-rays coming from this window will have a much bigger focal spot due to the entire length of the filament emitting the X-rays. These two types of X-ray beam are used in different applications. Well, once they were used, nowadays they almost always use the bigger X-ray beam, because the lower dimension beam, so the one with the finer focal spot, that is almost like a spot, was used, for example, the Baishar XRD cameras, while in the modern one they almost use always the wider beam, because you have more surface area, and due to the geometry of the modern X-ray diffraction machine, you can take advantage of all of the X-ray beam used. So the physical mechanism in which this type of tube works differ between the medical one here and this other X-ray diffraction tube, because in the medical tube you have a tungsten anode, and you usually apply a voltage of around 60 kilovolt to 120, but the hundreds of kilovolts are applied to, for example, tomography X-ray machine that use a really high energy, while this lower and smaller tube usually use up to 60-70 kilovolt, and because of this the voltage is not enough to excite the characteristic transition of tungsten, so you only get a Bremsstrahlung emission from this type of tube. This means that the X-ray emitted have an energy spectrum emitted that is a bell with the peak of the energy of the X-ray emitted that is at around 1/3 of the applied voltage to the tube. Well, in this other two tube, you need to have an almost spectrally pure wavelength due to the physical mechanism that is involved in X-ray diffraction. And so they used a specific metal as the target, and the voltage is always lower than 60 kilovolt, due to the fact that you want to excite the metal of the target with the closest energy to have the Bremsstrahlung spectrum that is imposed over the characteristic X-ray emission of the metal, so that you have the highest number of X-ray photon at the specific energy that you want. And so after the X-ray tube, a filter is placed that is made of a specific metal to filter out the lower and the higher energy X-rays, and so you can have a much higher monochromatic X-ray beam to do the different experiment. So now we're gonna disassemble these two tubes and see how the calling is performed. So let's start with this one. Here on the back you can see that 4 screws are used to keep this lower part together, and they simply came out. And then you can probably just take the tube apart gently, and you can see that it's composed of these two parts. So here you have the target. You can see here it's all made of copper to conduct heat better. And the target is flat, as you can see inside. The reason for the target being flat is that you have 4 windows and you want to have them the equal amount of X-rays, so the beam doesn't come perfectly parallel, but at a slight angle. While in this other tube you can clearly see that the anode is at a 45 degrees angle, so that the highest percentage of X-rays can be collected out of the window. So here you can see that the anode is this part here inside, and is cooled by a constant stream of water that is injected towards the anode by this plate. So you have that here and here there's the water supply, so water comes inside here and enters through this thick metal part and exit here in this slot. So this part should come out. Let's see. Here you can see this metal mesh to filter out any particles in the water. So the water comes out of this, goes into this slot, and then cools the anode, and goes down to the side, and enter this hole here, and gets out on this side here. Okay, let's now see the other X-ray tube. So this one is a Soviet one. It came with the documentation about it, as you can see. There's a copper anode, and it works up to a voltage of around 60 kilovolt, between 25 and 60. So this one opens using these flathead screws, and here you can see the inside. It had this rubber gasket that probably goes here. So you can see a clear difference between two tubes. As you can see, the Soviet one has an anode that is closer to the end of the tube, while this one, it's really strange because this one goes much deeper inside. As you can see, from this kind of technology, you can understand that they usually operate with a lot of power. The number of X-ray photons emitted by this tube is enormous compared to this more little one, and also they have really low energy. For this reason, you should not X-ray yourself using this kind of tube, because you'll end up like this Russian guy. To get such a damage, also exposure time plays an important role. But anyways, compared to, for example, a dental X-ray tube, it's a lot easier to get a higher damage with this kind of tube, due to the fact that an accurate dose it's harder to calculate, as low energy X-rays cannot be detected with the most part of a normal instrument, because they can be also absorbed by the probe itself. So you need something like an ionization chamber or a proportional detector that is capable of getting to the lowest range to be able and measure an accurate dose. If you have any other question, you can drop them down below in the comment, and bye.